Hey everybody, this is Emmy Jacob and working with Courtney Brown, and this is our Engineering 460 Digital Simulations Homework 9. So what is Homework 9? Basically what we want to do is we want to take a look at the Monte Hall problem, and what we'll do is we'll describe the problem itself, do a classical kind of mathematical approach to it, and then show you the solution of it, and then run it through MATLAB to kind of prove the Monte Hall problem through simulation and Monte Carlo. So let's take a look at this thing. So the Monte Hall problem is as follows. So a game show host basically has 3 doors, and behind those 3 doors he puts 1 prize and 2 duds. You obviously can't see what the duds are, where the prize is, and where the duds are at. And what the game show host does is offers you to choose one of the doors to pick, and then you pick that door, and before he opens that door to reveal what you have behind that door, he will or she will open up one of the remaining 2 doors, but he knows which door does not have the prize behind it. So he will open up a door that has a dud behind it. And then he offers you the choice. Do you stick with the original door that you chose, or would you switch to the door that is not open? So that at that point, what you want to do is statistically basically look at this and mathematically choose which door you want to go to. So here's the mathematics behind it. When you first look at these 3 doors, you have a 1/3 chance of it being behind door 1, 1/3 behind door 2, and 1/3 behind door 3. When you choose door 1, now we can add these probabilities together, and so there's a 1/3 chance behind here and a 2/3 chance of being behind one of these 2 doors. Now when the game show host eliminates one of the 2 chances, now your 2/3 chance basically concentrates on 1 door. So you have a 1/3 chance of you having chosen the first door correctly and a 2/3 chance of the next door, or the door that has not been opened, to be the correct door. So let's look at this and what it looks like actually mathematically, because you've got choice 1, choice 2, and choice 3. If you choose door 1, your game show host opens up door 3, and if you always switch, again, you should have a 2/3 chance of winning if you always switch. If you always switch, in this chance you don't get the door. If you choose door 2, opens up door 3 here, and you switch back to door 1, then you get to prize. That's 1 out of 2. And now if you do the same thing, you choose door 3. The host obviously knows where the car's at, so he chooses door 2, you switch, you win. So out of that, you see 2/3 of the time, you will actually win the prize. Let's see what that looks like in Monte Carlo. So in MATLAB, if we write this up using Monte Carlo, we basically can do this really quickly. We can set n, the number of iterations, to 100,000, set our counts for winning and losing, and then basically run a for loop. And in this for loop, we generate a random number. Now that random number is going to be obviously uniformly distributed, and we set if r is less than or equal to 1/3, then count it as a win. Else if r is greater than 1/3 and, or basically between 1/3 and 2/3, then count it as a win. If it's not, so if it's greater than 2/3, then count it as a loss. So we can run a probability of wins over the number of iterations that we've run, probabilities of losses over the number of iterations that we've won. Because what we said is that if you switch, and again, this is a scenario if the player switches the door every single time, if you switch, you're giving yourself a 2/3 probability of actually winning. Now let's look at the results in MATLAB. Now here we go with the same exact MATLAB code, and if we run this, we'll show you how we get our results. So here we go. We've seen now we've run 100,000 iterations, and the probability of winning gives us about 2/3, and the probability of losing about 1/3, which is what we expected based on our mathematical approach from the first part. So thanks for watching.